All right, so today we get to look at the definite integral as area. The last thing we talked about was Riemann sums, and we were approximating the area under curves using rectangles, and we would always do it between two intervals from A to B. As you can see in this picture right here, you can see one of our rectangles is right here, and again, approximating from A to B. So now we're going to go away from this verbiage of saying the area under the curve between x equals a and b, and we're going to notate it with a simpler mathematical symbol. So it says we're going to denote a shorthand to represent the same thing. We're going to use what we call the definite integral. Now, you guys have seen this integral sign before because we've done it with indefinite integrals in the very first sections of this unit. But now we're going to add on two limits of integration, and it's going to look like this, where we have the integral from a to b of f of x dx. And again, this is the same thing as saying the area under the curve between a and b of this function. So similarly to first semester, how we were always talking about how the derivative is the same thing as the slope of the tangent line, in second semester we will talk about how the integral, is the same thing as the area under the curve. So whenever I mention an integral, I always want you to visualize this idea of area underneath the curve. Excuse me. And again, let's talk about why that is. So I like this paragraph. It helps to explain it a little bit. It says the f of x represents the height of any one of the rectangles, kind of like how we were talking about in Riemann sums. So f of x is how tall this rectangle is. And dx represents the width of any one rectangle. So remember, when we were looking at Riemann sums, our widths were maybe like 1 unit long, or 10 units long, or a half of a unit long. But we said if we wanted to get more and more accurate, we needed to make these smaller and smaller and smaller, and that the exact area under the curve would be as if we had an infinite number of rectangles that we fit into this area in between A and B. So because of that, we push that width to be smaller and smaller and smaller and smaller. And so this dx is very, very, very minuscule, like incredibly small width. And so if you multiply the width of the rectangle by the height of the rectangle, you get f of x times dx, which ends up being the area of the rectangle. And what the integral does after that is that the integral adds them all together. So it takes these infinite number of rectangles, finds the area of every single one, and then adds all of them together. And then A always represents the starting place, and B always represents the ending place. A couple generic things, if you want to copy these down into your notes, these will become important as we go forward from here. If we are reading from left to right, you're going to get that our widths are positive values. If we're reading from right to left, you're going to get that our widths are negative values. So, for example, if A is less than B, meaning like if you start from the left and it's 2 and you go to the right, which is 5, versus if you go from 5 to 2. So depending on which way you read it, you're either going to get positive values or negative values. And then if the function is above the x-axis versus below the x-axis, it will depend on whether or not we get these areas to be positive or negative. And we'll kind of see that as we're looking at it a little bit more in detail in a minute. Excuse me. So it says there are 3 more rules which will make sense to you. The first one, if I'm taking the integral from a to a, meaning my left endpoint is a number and my right endpoint is that exact same number, then the area is 0. And I hope that makes sense, because if you started at like 2 and end at 2, you didn't go anywhere. And so since you didn't go anywhere, you don't have a width. And if you don't have a width, then you don't have an area. Therefore, area is 0. This one says if you're reading the area from A to B of f of x dx, it's the same thing as reading it backwards from B to A. The only difference is that it becomes a negative area when you read it backwards. Similarly to what we were just talking about up here. So typically we like to read it from smaller number to bigger number. If it's backwards, we would just flip it and make it negative. And last but not least, if you're reading an integral from A to B, and then you stop at B and add another integral where you're picking up again at that same x value B and going all the way to C, it's the same thing as if you never stopped at B to begin with. So you can go A to C and add together all the areas from A to C. All right. So let's do some examples together. We have this picture. Notice that all of the lines are straight lines and or circles. Over here we have this half circle. Everything else, however, is straight lines, which means we're able to find the area because we're just working with rectangles and triangles and circles. And these are all things we've known how to take the area of for quite some time. The first one says, what is the integral from 4 to 4 of this function? Remember we said that if we start at a number and end at the same number, it means we didn't go anywhere. And if we didn't go anywhere, then we did not accumulate any area. So this first one has an area of 0. There is no area under a curve that doesn't go anywhere. The second one says the integral from 0 to 3. So let me come over here to my graph. I'm going to look at the area from 0 to 3. So here's 0, 1, 2, 3. And it looks like I have a rectangular area I can find. And I have this triangular area I can find. So I know how to find the area of a rectangle. It's base times height. So my base is 1, my height is 2. Therefore this area is 2. My triangle is 1/2 base times height. So the base is 2 and the height is 2. So 2 times 2 is 4, but it's only half of that. So it's also 2. Therefore, if I'm adding together these two areas, I get 2 plus 2 to equal 4. Excuse me. And the last one, example 7, says the integral from 0 to 6. So I already have the integral from 0 to 3. If I want to continue, I can add on to 4, 5, and 6. So I also want to add in this triangular area. Notice, by the way, that it's below the curve. So we're reading it in the right direction from smaller number to bigger number. But if it's below the x-axis, it becomes a negative area. My base is 3. If you count these, it's 1, 2, 3. My height is -1. Excuse me. So the area of this triangle is a base of 3, a height of -1. So that's 3 times -1 is -3. And then it's a triangle, so divided by 2. So -3/2. Again, because it's below the x-axis. If I add all these together, I get 2 plus 2 to equal 4. And then if I add all the way to 6, I have 4 minus 3/2, which is 4 minus 1.5. And 4 minus 1.5 is 2.5. So the area from 0 to 6 would be 2.5. 2 positive numbers plus that negative number. All right. I know we're going out of order, by the way, so just kind of follow along in those notes that you have. For this one, it's the integral from 0 to 1 of f of t dt. All right, 0 to 1 would be there, just that rectangle. That has an area of 2 units. The next one, the integral from 3 to 6. That would just be this piece right here. All right, so from 3, if we start at 3 and integrate all the way to 6, the area under this curve, we talked about on the last slide that it was 3/2, and it's negative since it's below the curve. So that's a -3/2. Or -1.5. It's up to you on how you want to write it. And the last one is the integral from 6 to 10. So 6 is here, 10 goes all the way over here. So it's essentially this semicircle. The area of a semicircle is pi r squared over 2. So the radius of the semicircle is 2. If you look at the center of it, it goes up 2, it goes to the right 2, and it goes to the left 2. So the radius must be 2. The area of a circle is pi times the radius squared, so pi times 2 squared. But since this is only half of a circle, we have to divide it by 2. If it was a quarter of a circle, we would have divided it by 4. So 2 squared is 4, 4 times pi was 4 pi, 4 pi divided by 2 is 2 pi. So that's number 8. Number 3, again, kind of all over the place. The area from 1 to 3. So here's 1, 2, 3. Again, we already found that area of that triangle earlier. It had a base of 2 and a height of 2, which was 2 times 2 is 4. But then since it's a triangle, we divided that by 2, and we got 2. Notice on number 6 that this one's actually written backwards. So instead of written from 3 to 6, from smaller number to larger number, it's written backwards from 6 to 3. When that happens, we always fix it. So I don't ever want to see an integral written from a larger number to a smaller number. So in order to fix this, because remember, if we're reading it backwards, essentially what that's doing is that's giving us like a negative reading on the x-axis. And so since it's giving a negative reading on the x-axis, we can fix this by flipping it upside down and making it negative. So this is the integral from 3 to 6 of f of t dt. And we throw that negative in front of there. As soon as we flip it upside down, we can put a negative in front. So the integral from 3 to 6 of this function and making it negative. We already talked about how the integral from 3 to 6 on the last 2 slides. We talked about how that area is a negative 3/2. But if I plug that into this function, I get a negative 3/2, which turns into a positive 3/2. So notice that if we're reading the x values backwards, but then in addition to that, the function is below the x-axis, then as we read it backwards and it's below it, it ends up creating a positive area again. And then last but not least, number 9. Again, let's flip it. So it's the negative integral from 6 to 10, f of t dt. And we did this one on the last slide as well. This is that semicircle right here. We said it had an area of 2 pi. So this is just going to be negative 2 pi. All right. I encourage you to pause the video and try some of these ones on your own. So I'm going to let you guys try 10, 13, and 16 on your own. And then 19 we'll look at together because that one has a little bit of a trick to it. So try those other 3 on your own and we'll come back together again for that last one. All right, so for this first one, we had already calculated all these areas. Again, I just added them all together. So from 0 to 10, that's the 4 we already calculated minus this 1.5 plus the 2 pi. So 4 minus 1.5 was 2.5 plus 2 pi. You can't combine those, so we'll just write them like that. 2.5 plus 2 pi. This one from negative 3 to 0, that's not written backwards because negative 3 is a smaller number than 0. That's technically written forwards. So I came over here and I divided it up into shapes I knew how to find the area of. So I had a rectangle down here at the bottom that was 4 units. And then I had a triangle right on top of it that was 4 units. And then I had this tall, skinny triangle right here that was 6 units. So 3 units. Finding the areas of all those and then adding them together from negative 3 to 0 gave me 3 plus 4 plus 4, which is 11. And then 16. Again, this one's written in the correct order from negative 4 to 0 because negative 4 is smaller than 0. And the only thing we added on over here was this little negative piece of area that was a negative 1/2. So essentially taking the area of 11 that we already had and then subtracting a half from it gave us 10.5. Number 19. Number 19 wants the integral from 0 to 10. So back over here on this side again, from 0 to 10 of the absolute value of the function dt. Now, remember that the absolute value, all that it does is that it takes negative values or negative areas and makes them positive. So if I look between 0 and 10, from 0 to 3, these values are already positive, so I don't have to worry about it. From 6 to 10, these values are also already positive, so I don't have to worry about it. However, in between those, from 3 to 6, I have this piece of my function that's below the x-axis. The absolute value of that function would look like this, where it has a positive 1.5 units of area. So this last piece, number 19, is essentially asking for the area of this red shaded region. So 4, but instead of subtracting the 1.5, we're going to add it because it's the absolute value of this function, and then plus 2 pi. If I add all those, I get 4 plus 1.5 plus 2 pi, and that gives me 5.5 plus 2 pi. And again, that's as far as I can go. Can't combine those two things together. All right, I encourage you to pause the video again. I will do this math, and then we'll come back together again and check our answers, but I want you guys to try and do these 4 on your own first. Be very careful with that last one and try to understand. It's a little bit different than the one on the previous slide. On the previous slide, the absolute value bars were inside of the integral. It was the absolute value of the function. On this one, the absolute value bars are outside of the integral. So it means to find the integral first and then take the absolute value of the answer. So, like I said, I'll let you guys try that one, and then we'll come back together again and talk about it. But for sure, try 11, 14, and 17. Pause the video now. All right, so I'll show the other two in just a second, but this was all I could fit on the screen for right now. On number 11, it's the same thing we already found out previously. We knew it was 2.5 from 0 to 10. It's 2.5 plus 2 pi. But because it's backwards, we have the larger number written first and then the smaller number. We just had to fix it by flipping it upside down and making it negative so we could read it forwards. And when we do that, it becomes a negative 2.5 minus 2 pi. For number 14, same thing. We already knew the area between negative 3 and 0 was 11. Since we're reading it backwards, 0 to negative 3, I flipped it upside down, made it negative, therefore it becomes a negative 11. Let me do the next one, and then we'll talk about that one right now. All right, so for 17, excuse me, we had this negative, we're going all the way from negative 4, by the way, all the way to positive 10 way over here. So we have this little negative 1/2 piece, plus 11, plus 4, minus 1.5, plus 2 pi. So if I add up all of these together, I get 13 plus 2 pi. And last but not least, for number 20, again, we talked about how the absolute value bars on the previous example were inside the function. If this was the same type of example where the absolute value bars were inside the function, we would have taken this little negative 1/2 piece and flipped it above the x-axis, then taken this little negative 1.5 piece and flipped it above the x-axis and added them all together. This is different, though, because this is saying on the inside of these absolute value bars, to find the integral from negative 4 to 10, of this function, which we already did in example 17, that's this answer right here. And once you find the integral, take the absolute value of that, of the answer. So the answer is 13 plus 2 pi. Well, that answer is already positive, so the absolute value will have no effect on that answer because it's already positive. So the answer to number 20 is also 13 plus 2 pi. If the answer to number 17 were a negative value, then by putting absolute value bars around it, it would have become a positive value for 20, but because it's already positive, it does not affect it. All right, numbers 12, 15, 18, and 21. I will let you guys attempt these ones, so do me a favor and put a pause on the video while you guys do that. All right, so number 12. This one they're asking for a little bit of a different interval, and so I had to kind of regroup how I found the area earlier. Earlier I had one big giant triangle up here and a smaller rectangle down here, but because they're just asking from negative 1 to 0 now, I had to regroup what I knew and kind of change it up a little bit. So negative 1 to 0 is still reading it forwards because negative 1 is smaller than 0, so we don't have to fix that. This little rectangle down here at the bottom had an area of 2 units, and this one right here had an area of 1 unit. So we just added them together to get 3. For number 15, from negative 4 to negative 3. Again, this is correct. This is the correct order from smaller to larger. Negative 4 to negative 3. So from negative 4 to negative 3, we had an area that was below the x-axis, and it was a unit of 1/2. Therefore, it's negative 1/2, negative 0.5. For number 18, this is kind of anticlimactic because we just did it on the previous screen with a larger problem. But the integral from 0 to 10, we already said, was 2.5 plus 2 pi. And throwing the absolute value bars around the outside of that just says, once you've found the answer for the integral, make it positive. And ours already was. Number 21 is a little bit more intense because we have this 2 in here. So I want to talk about it in pieces. The first thing is that this integral is not in the correct order. It's from 10 to negative 4 instead of from negative 4 to 10. So I flipped it upside down and I made it negative. That's the first order of business. Then we have to look at the fact that it's the absolute value. So notice that the absolute value bars are inside of the integral with the function. So when I have the absolute value, all these pieces that are negative reflect up here to become positive. So this is a positive 0.5 units of area, and this is a positive 1.5 units of area. All right, and last but not least, we have this 2 in front of it, and essentially what the 2 does is that it's a constant multiple, and what constant multiples do is that they will they will essentially multiply all of your areas by 2. So I won't draw it out because it would be too much work probably, or wouldn't fit on the graph properly. But all these areas essentially get multiplied by 2 because all the y values get multiplied by 2. So for example, this point, instead of going through negative 4, 1, it would go through negative 4, 2. And then that triangle would have an area of 1 unit instead of 1/2. This one, instead of going through negative 2, 6, would have gone through negative 2, 12. And then this area over here would have been 6. And all of these would have doubled as well. So essentially what it does when you multiply by 2 to a function is that it increases all of the y values by 2, which means that all of these areas are going to be increased by 2 as well. So we can worry about that 2 actually at the very, very end. If I add together all of these areas and then multiply by 2 and then make it negative, that would be my final answer. So let's do that. If we add together all of these, I think last time we said that it was 13 because this was 11. 11 plus 4 was 15. Oh, no, wait, because we're still adding. Just kidding. So over here on this side is 11, so that's 7, 8, 9, 10, 11, plus 4, there's 15, plus 1.5, there's 16.5, plus this half, there's 17, and then 17 plus 2 pi. So that's what f of t is from negative 4 to 10. So we still need to make it negative, and we still need to multiply it by 2, but so far we have 17 plus 2 pi. So if we make it negative and distribute the negative 2, this would give us negative 34 minus 4 pi. And that's the final answer. So again, all the y values get multiplied by 2, which means our area is multiplied by 2. And because it was written upside down from the very beginning, we had to fix that by making it a negative. All right, new type of problem. We're finally away from that graph now. So these problems are essentially doing the same thing. The only difference is that instead of you having to calculate the areas, they're giving you the areas. That's kind of nice. So this first one says, what's the integral from negative 2 to 5 of f of x plus g of x? Well, I know the integral from negative 2 to 5 of f of x is 18. There's 18 units of area underneath that curve. And I know the integral from negative 2 to 5 of g of x is 5. There's 5 units of area underneath that curve. So if I add these two functions together, it's just like adding their areas together. So 18 plus 5 shall give me 23. For the next one, same problem, negative 2 to 5, f of x plus g of x, but this time they want us to subtract h of x. So we have 18 plus 5 minus a negative 11. Let me say that one more time. 18 plus 5 minus an area of negative 11. So 18 plus 5 minus a negative 11 becomes 23 plus 11, so 34. For number 24, a couple things with this one. Number one, it's upside down, 5 to negative 2 instead of negative 2 to 5. So let's fix that by flipping it. So this is a negative integral from negative 2 to 5 of 4g of x dx. Now, I know that the area underneath the curve of this function from negative 2 to 5 of g of x is 5. But it's also going to be negative because we flipped it, and it's also going to be multiplied by 4 because we have a constant multiple there. So we have a negative 4 that needs to be multiplied by this area for g of x, which is 5. That gives us negative 20. All right. Number 25. Now, this one we have to be a little careful about, and they love to ask this question on the AP test. Not a ton, but they have asked it before in the past. I want to make sure you guys know how to do it. So this is a little different than the constant multiple. So in the last one, remember that when we multiplied by 4, for example, on example 24, all that it did was change all my y values, and all my y values got multiplied by 4. And when you do that, that doesn't change the area except for the fact that it's like a scalar multiple. So it just multiplies the area underneath the curve by that value. This one is different. We're not multiplying by 2 in this case. We're adding by 2. Now remember from all of our function transformations, when you add 2 to a function, it technically shifts the function up 2. So let me just show you what that looks like. I'm going to make up a function for g of x. I have no idea what it actually looks like. But let's say g of x looks like this. All right, this is g of x. So here's my area under the curve. All right, and so let's say this area is equal to 5. Well, if I add 2, all that it's going to do is it's going to take my function and shift it up 2, like this. So notice this red area that I've just highlighted is the same area I had before as the purple one. So this is still an area of 5 units. The only difference is that now the area under the curve includes this rectangle down here at the bottom. So this rectangle down here, I guess I should color it a different color. This orange rectangle down here at the bottom just got added to the area under the curve. So this one didn't change its shape. All that it did was move up, and so it's still 5 units. But now I've added this rectangle underneath the bottom, and I have to take into account how much area that has added. So you have to figure out how wide the rectangle is. So that's going to be what the length is from A to B, which obviously this is not drawn to scale because -2 to 5 would be all the way from over here to over here. But you get the point. We need to figure out how long it is and then how much height was added to it. So in this case, it would be +2. And if you can figure out the height and the base, then you can multiply them together to find the area. And once you do that, then you'll have your answer. So I'm going to rewrite this really quick just so you guys can see it as -2 to 5 of g of x dx plus the integral from -2 to 5 of 2 dx. Now, we already know the integral from -2 to 5 of g of x is 5, plus this rectangle that we just looked at on what I just erased has a height of 2 because it was shifted up 2, and then -2 to 5, if you think about how much distance is between -2 and 5 on a number line, there would be 7 units. So from -2 all the way to 5, it would be a base of 7 with a height of 2. So technically we're adding in 14 units of area. So when I do that, I get 19. For number 26, it's the same thing. Integral from -2 to 5 of f of x dx. Only this time we're moving it down 6 units. And when we move it down 6 units, it's like subtracting 6 units of area. It's like subtracting a rectangle that's 6 units high. So we'll do minus the integral from -2 to 5 of 6 dx. We know that the first part, -2 to 5 of f of x, is 18. Minus, again, the base of this rectangle has a length of 7, because -2 to 5 is 7 units long. And the height is 6. So this is 18 minus 42, which ends up being -24. And number 27 is a little different still. So 25 was a vertical shift up 2 units, therefore it added a rectangle below it that was 14 units in area. Number 26 was a vertical shift down 6 units, therefore it subtracted 42 units of area because the rectangle had an area of 42 units. This is not a vertical shift. When you have a number being added or subtracted inside of a function, it's a horizontal shift. So remember that subtracting 2 inside of this function is essentially shifting the rectangle 2 units to the right from the original function. So I've drawn an example here. Let's say that we have this area, and from -2 to 5, it's below the curve. H of x is -11. So from -2 to 5, this function has an area of -11. If we take that function and shift it 2 units to the right, it would look like that. So again, it's the exact same function. Notice that -2 moved to 0 and 5 moved to 7, but the shape of the function did not change. All it did was move the function 2 units to the right. I know mine's not perfect, but imagine with me that it didn't change. And so this -11 units is still -11 units, it's just in a different location. But notice that the limits of integration changed with it. So from 0 to 7, it changed from -2 to 5. All of those limits moved as well. So 0 to 7 are my new limits of integration, but the area itself did not actually change. Therefore, the area is still the same as it was when it was from -2 to 5, which is -11. All right, and then 28, 29, and 30. Again, this is a horizontal shift of the function g of x 2 units to the left this time. So we had it from negative 2 to 5. If you move negative 2 2 units to the left, that's minus 2, gets you to negative 4. If you move 5 2 units to the left, that gets you minus 2 to 3. Therefore, again, this is the same exact function that's just been shifted horizontally in the coordinate plane. So this 5 units of area is still equal to 5 units of area, just in a different place, but still 5 units. For f of x from, what does it say, 5 to 8. This one's a little different. Notice that none of these limits of integration go from 5 to 8. They're all either from negative 2 to 5, negative 2 to 5, negative 2 to 5, or negative 2 to 8. So we're going to have to do some kind of a combination to make it equal what we want it to equal. So notice that this one is the widest integral. It goes all the way from negative 2 to 8 of f of x dx. And we have this one over here that's dealing with f of x, and that's from negative 2 to 5. So I kind of want to just draw it out for you. We have this integral all the way from negative 2 to positive 8. We have this function. And it says that the area is 0. So I'm going to draw it like this. Ooh, that's ugly. So here's why I'm going to draw it like this. This piece of it says that the integral from negative 2 to 5, the area under the curve of this function is 18 units. So I'm going to say from negative 2 to 5 that it's 18 units. But this one says if you go all the way from negative 2 to 8, all the way from here to here, that it actually has an area under the curve of 0, which means there must be some really, really big negative piece that's canceling out this positive piece. So this one must have an area of negative 18. All right, and so if I just want to know the area from 5 to 8, graphically, you can look at this picture of this graph I just drew and notice that from 5 to 8, it must have an area of negative 18 because that's how it has to work in order for these to add to 0. But algebraically, if you didn't want to have to draw out the graph and try to figure out what it looks like that way, you would take the larger interval, so take the entire thing from negative 2 to 8, and subtract away or take away the piece that's the smaller interval, and that will leave you with whatever's left. So if I take the whole thing from negative 2 all the way to 8 and subtract out the piece I know from negative 2 to 5, it will leave me with what's left from 5 to 8. So algebraically, it looks like this. Well, I'll show you two ways. We could either say the integral from negative 2 to 5 of f of x dx plus the integral from 5 to 8 of f of x dx is equal to the integral from negative 2 to 8, almost as if we didn't stop at that breaking point, of f of x dx. So notice from negative 2 to 5, then we pick up again from 5 to 8. That would give me from start to finish, negative 2 to 8. Now again, we know this piece, and we know this piece, and we're looking for this piece. So if this is an equation, to find this piece in the middle, we would subtract this one over to the other side. So the integral from negative 2 to 8 of f of x dx is equal to 0. So this piece is equal to 0 that I just wrote right there. And then if we're going to subtract this piece over to that side as well, the integral from negative 2 to 5 of f of x dx was 18. Therefore, 0 minus 18 is negative 18. Final answer. So again, you saw it graphically, and then here's what it would look like algebraically if you were going to look that way as well. All right, I'm going to erase this so we can look at number 30, because number 30 might need a little bit more space. All right, on number 30, a couple things are happening. Number 1, we have a horizontal shift happening, so we need to analyze these limits and make sure nothing changed in terms of the area. And then number 2, we also have a vertical shift happening of plus 3. So this minus 3 essentially says that we took the function f of x, excuse me, we took the function f of x and we shifted it 3 units to the right. So if we had this originally, negative 2, if you shift it 3 units to the right, would be negative 2 plus 3, which is 1. That's correct. And then 5, if you shifted it 3 units to the right, would be 5 plus 3, which is 8. That's correct. So this f of x minus 3 does nothing to the area under the curve. All that it says is I moved my area 3 units to the right. I didn't change the area. I didn't stretch it. I didn't shift it up or down. All I did was move it horizontally. My limits of integration changed with it, so it's not a problem. So my area was 18. So this piece would still be an area of 18. So let me write that out. So this is the integral from 1 to 8 of f of x minus 3 plus the integral from 1 to 8 of 3 dx. So like we said, this piece is still 18. The integral from 1 to 8 of f of x minus 3 is just this function shifted horizontally in the coordinate plane 3 units to the right. That's that. Plus, remember that this one is adding a rectangle underneath since it's a vertical shift. It has a height of 3 units, and if you look from 1 to 8, that has a base of 7. So it has a base of 7 units and a height of 3 units. That means it's adding on 21 units, 3 times 7. So if I add these 21 plus 18, I get 39 units of area underneath that curve. All right, so we're going to stop there for today. We only have a few more examples, but we'll save those for tomorrow.